Nice to meet you. I'm Prof.Joun, working for GNU in Korea. The topic of this lecture is deformation, strain, and rate of deformation, with emphasis on application to solid mechanics. The contents and the approaches of this lecture were much affected by these three references. The first reference is Continuum Mechanics, published by McGraw-Hill as one of sham series, which involve summarized theories with many good examples. The second reference is aimed for teaching graduate students focused on theoretical plasticity. The third reference was written for teaching senior graduate students the finite method coupled with solid mechanics. First of all, we have to study how to describe material in a mathematical form. Of course, material is considered as a set of infinite number of particles. As can be seen in this figure, material is symbolically described by balloon with surface. There are two configurations of the material, that is, initial and final configurations. The initial configuration describes the material before deformation, while the final configuration on right side describes current configuration of the material. Of course, there are two ways of describing the material and its deformation, which can be identified by position of particles. The position, that is, coordinates of particles, can be identified by two ways. The first way is based on initial configuration and initial coordinate system, which is described by logic characters x1, x2, and x3, and called material coordinate system. The vector, bold and capital letter X, expresses the position, that is, coordinates of the particle. And the coordinates are the most basic geometric quantities of the material, which describe the shape or configuration of the material, of course. A small character is used to describe the special coordinate system, which is important to identify the position. And that is the coordinates of particle in current configuration, represented by point P prime in this figure. P prime in this figure was mapped from point P in the material coordinate system for the initial configuration by a non-mapping function. Of course, the mapping function describing the deformation is a major target of the mechanics, which is governed by nature as well as intention of human being. We'd better use this kind of Cartesian or rectangular coordinate system for simplicity and generality to describe the theory. Of course, there are some special curvilinear coordinate systems which can be used for solving some specific problems by hand calculation. In the past, when the researcher had depended on hand calculation, such complicated coordinate systems had contributed to studying the mechanics for theoretical advances. However, their contribution to solving practical problems were very weak. Currently, numerical analysis technique is very practical, which is based on discretization of the material into finite element or grid system. So very complicated or specially configured geometries can be mathematically described by the simple and general Cartesian coordinate system. The origins of the material and the special coordinate system can be different, of course. The relative difference of them is identified by constant vector b, as can be seen in this figure. However, we will set b equals 0 soon, because non-zero b only increases the complexity. Of course, when we set b equals 0 in graphics, two configurations should be superimposed, which causes geometry confusion. So we will maintain using this setup with b equals 0 emphasized here. Okay, and now we know that there are 2 points representing the material and some currently unknown relationship between them. That is a non-mapping function. Now we are interested in how to describe position, that is coordinates of the point, in a mathematical form. Consider a non-mapping function based on the continuum mechanics. There are 2 ways to reach this score. The first way is the material description of coordinates. In this method, we describe the current coordinate as a function of initial coordinates and time parameter. The second way, called the special description of coordinates, expresses the initial configuration or initial coordinates in terms of current coordinates and time parameter. Of course, we have to assume one-to-one correspondence between 2 material points, P and P prime. It is simple, but very important. The one-to-one correspondence is very important. Okay, this point should map to this point, and it should be inversely mapped to its origin point. That is the meaning of the one-to-one correspondence. It is very simple. This assumption can be acceptable in most macroscopic mechanics. The material following this assumption is called continuum. During plastic deformation of material, dislocations occurs, which violates the assumption of one-to-one correspondence. So when we are interested in such macroscopic behavior of material, our theory cannot be applied. Anyway, we are studying mechanics of continuum from the macroscopic viewpoint. Now we are going to study how to describe the displacement. Of course, the displacement is geometric description of the difference in coordinates of 2 points, that is P prime and P. And there is 2 ways of describing the displacement mathematically. The first one is the material description of displacement. In this method, the displacement is described by a function of the initial coordinates, the material coordinates. The second way of describing the displacement is a special description of displacement, which uses a function of spatial coordinates. So that means in this case, the displacement is described in terms of the current coordinates. And I'm going to define the the gradient here. There are of course two ways of describing the gradient. The first one is material displacement gradient, which is defined by the partial differentiation of the displacement with respect to the material coordinates, the initial coordinates. And the second way of describing gradient is the special displacement gradient, which is defined by the partial differentiation of the displacement with respect to the current coordinates. Okay, we are going to study a deformation of a differential line segment, sometimes called line element, and to define the deformation gradient tensor. I added two differential line segment like this to the figures employed previously. Of course, you know the x in material description is a function of the material coordinates, large x. And so we can apply the partial differentiation of the special coordinate with respect to the material coordinates. So this is a matrix, a tensor quantity. So we usually we define this matrix using large capital F, which is called material deformation gradient tensor. Of course, it can be described in this way, that is xi comma j following the initial notation. There is another description of the deformation gradient tensor. That is a special deformation gradient tensor. Okay. From the differentiation of the material coordinate with respect to the special coordinates in a similar way with the material deformation gradient tensor. Now, of course, we assume that the 2 points are one-to-one corresponding. So in this case, the partial differentiation of the special coordinate with respect to the material coordinate is non-singular. So there is the inverse matrix of F, that is material deformation gradient tensor. So we can derive this relationship between the material deformation gradient tensor and special deformation gradient tensor. Up to now, we have used two different coordinate systems which have different orientations for generality. From now on, we'll better use the same coordinate systems having the same orientations as can be seen in this figure. Of course, their origins are perfectly identical because we already assumed the vector b equal to 0. However, we'll better keep using this figure to exclude some confusion between initial and final configurations of the material. Now, let me define the unit basis vectors E hat and E for the material and special coordinate systems, respectively. Of course, they are identical as described by this vector equation. Inner products of two unit basis vectors, EI and E hat J, can be replaced by delta I large character J, that is canonical delta. We have used capital letters for indices in material coordinate system, while small characters for those in special coordinate systems. Okay, displacement vector can be expressed in material description by this vector equation, which is a function of material coordinates. This vector equation can be expressed by this equation using summation convention in initial notation. To obtain ith component of the displacement vector, we have to apply inner product of EI with both sides of this equation. Then these two inner products can be replaced by delta ij, and this term by delta I large character J. The expression of this equation is okay and formal. However, we will sometimes use this expression together with this formal expression. Let me show you another example. This is the material different gradient tensor. Okay, so this tensor can be expressed in two ways, by this equation and this equation. Now we are going to define deformation tensors, which are very important in mechanics. First, we will find some relationship between line segments and material and spatial coordinate systems. We already derived these equations to define deformation gradient tensors. Understanding these equations, the scale length of the differential line segment in material coordinate system, denoted by scale dx, can be calculated from inner product of the vector dx and itself. Substituting this relationship into this equation, so we can derive this equation and define Cauchy's deformation tensor, which is sometimes called left Cauchy green tensor. In the same way, we can define Green's deformation tensor, which is sometimes called light Cauchy green tensor. In this slide, we will define finite strain tensors. Using the deformation gradient and Green's deformation tensor, so we can develop this equation for the difference in scale length of differential line segment defined in material and spatial coordinate systems. And now we can define Lagrangian finite strain tensor by this equation. We already studied the relations between material displacement gradient and material deformation gradient tensors. Applying this equation to this equation, we can express the Lagrangian finite strain tensor in terms of displacement gradient. In the same way, for the spatial coordinate system, so we can define the Eulerian finite strain tensor by this equation. Now let me define infinitesimal or linear strain tensors. Assuming that the material displacement gradient is too small compared to the unity, we can delete the higher order term, and then we can obtain the Lagrangian infinitesimal strength tensor, like this. In the same way, from Eulerian finite strength tensor, so we can neglect the higher order term to define Eulerian infinitesimal strength tensor like this. Of course, under the condition that the deformation is small, when both the displacement and displacement gradients are small, then the Lagrangian infinitesimal strength tensor is the same with Eulerian infinitesimal strength tensor. Now let us define relative displacements, linear rotation tensor, and rotation vector. In this figure, we define du, that is relative displacement. Now we are going to express it into mathematical descriptions, that is Lagrangian and Eulerian descriptions of the relative displacement. Partial ui, partial xj, that is the material displacement gradient, which can be decomposed into two terms. One is symmetric and the other is symmetric. The former was already defined as the linear Lagrangian strength tensor. The latter is defined by linear Lagrangian rotation tensor. Using Lagrangian rotation tensor, so we can define Lagrangian rotation vector by this equation. Now, summing the linear Lagrangian strength tensor equals 0, then we can relate the relative displacement with differential line segment in terms of the rotation vector. In the same way, we can derive the equivalent equations for the Eulerian description of relative displacement to the Lagrangian description of relative displacement. Now let us check the meaning of linear Lagrangian strength tensors. We'd better take two parts into consideration, and that is normal strain and shear strain. Let us assume that the length of the differential line segment in material and special Continuum systems are the same, based on the assumption of a small strain and small deformation. Dividing the scalar length of differential line segment onto both sides of this equation, so we can obtain this equation. In this equation, the m hat means the directional vector, which is defined by this equation. And the first inner product of tensor and directional unit vector in this equation means the vector equivalent to the tensor on a plane normal to the vector m hat. The second inner product of the equivalent vector with unit vector m hat produces the normal component of the tensor along the directional vector m hat. So, like term of this equation means normal component of the tensor quantity along the directional vector m hat. Now let us check for some specific case that dx1 and dx3 are equal to 0 and dx1 is equal to 1. So applying these conditions onto this equation, so we can obtain this equation, implying that element L22 means normal strain along the x2 axis. Now let us check the meaning of the off-diagonal terms of the tensor quantity using the definition of partial differentiation and and these graphics. Let us consider a line segment on which only delta xi is allowed to change along the line element. The difference of the jth component of displacement between two endpoints divided by this length means tangent theta ij, which is equal to theta ij in linear elasticity. In the same way, we can express the first term as theta ji over 2. When you apply this approach for some specific components, for example, L23, you can understand the meanings of the up-down term of the linear Lagrangian strain tensor in a much easier way. Now, let us consider the meaning of finite strain tensors. A stretch ratio is defined by small dx, large dx, which is a measure of the extensional strain of a differential line segment. Scaled stretch at a point in a material cone system for the differential line segment along the unit vector m hat is defined by this equation. Because Green's deformation tensor has the relationship with a Lagrangian finite strain tensor, so we can link Lagrangian finite strain tensor with the stretch using this equation. From this relationship, we can imagine the meaning of the finite strain tensors. Of course, it's not easy. For example, let us consider a special case that m hat equal to E2. That is, m1 and m3 are equal to 0 and m2 equal to unity. Applying these conditions, this equation shrinks to this equation, where only the tensor component L22 remains. From this relation, we can imagine the geometric meaning of the tensor component L22. Yeah, of course, L22 has direct influence on the stretch in the x2 direction. Okay. Now let us consider the meaning of the up-down term of finite strain tensor. This equation shows the relationship between the tensor elements and shear deformation, which emphasizes that downward terms and off-downward terms are both coupled in terms of shear deformation. However, off-downward term is the major factor affecting the shear deformation and shear strain. So some detailed derivation of this equation was skipped because the procedure of the deriving these equations is a little complicated, and its derivation itself is not meaningful for further study. Please refer to the recommended books. Now we are going to define stretch tensor and rotation tensor, which are very, very important in mechanics. Following Cauchy's theorem of polar decomposition for a non-singular matrix A, we can express it by a multiplication of two matrices, in which one is symmetric and the other is orthogonal. It is interesting to note that there is two options of polar decomposition according to the position of the orthogonal matrix. Okay, when we apply polar decomposition to the deformation gradient f, which is of course non-singular, f can be expressed by Rs or Tr. R is an orthogonal matrix called rotational tensor, implying that R governs the rotational motion of the material. S is called light stress tensor or right causes tensor, while T is called left stress tensor or left causes tensor. Both stress tensors are positive, definite, and symmetric. This equation can be expressed again like this using indicial notation. Therefore, a differential line segment in material description can be stated by this equation, which means that the deformation consists of a sequential stretching by stress tensor S and rotation by rotation tensor R, to be followed by a rigid motion to the point P in the first case, and that the rigid translation to P is followed by rotation by rotational tensor R, and finally the stretching by the stretch tensor T in the second case. Now, let us focus on the meaning of the stretch tensor. Substituting the polar decomposition of the deformation gradient tensor F, that is Rs or Tr, into the definitions of the tensors G and Xi inverse, we can express them in terms of tensors S and T after some simple arithmetic operational matrices. Post-multiplying the transpose of rotation tensor on both sides of this equation, so we can derive this equation, which is important for developing the theory in this page. We already explained the geometry meaning of the polar decomposition of deformation gradient tensor. Now, let's consider eigenvalue problems for two stretch tensors, which are formulated by these equations, having different eigenvalues and eigenvectors. Substituting this relationship into this eigenvalue problem, we obtain this equation. Now, let us multiply the transpose of rotation tensor on both sides of this equation to obtain new eigenvalue problem like this. Comparing this new eigenvalue problem with the eigenvalue problem for the light stress tensor, so we can conclude the two eigenvalues lambda hat k equal to lambda k. The two eigenvalues are the same. And the two eigenvectors should meet this transformation law. Now, let's calculate eigenvalue for Green's deformation tensor. Inner product of the G and the kth eigenvalue of S, that is right stress tensor, is equal to scaled matrix S post multiplied by the same eigenvectors. Because this matrix multiplication results in the identity matrix, it always holds. S is symmetric, so we can replace the second stretch tensor S by its transpose. Now, we can find more meaningful form like this after some arithmetic arrangement. You know this eigenvalue problem where n hat k is normalized. After all, we derived this eigenvalue problem for the tensor G, which means that its eigenvector is the same with that of the right stretch tensor S, and its eigenvalue should be scaled eigenvalues of the stretch tensor S. Now we are going to study the deformation of an areal element in three-dimensional space. The areas of parallelograms defined by two differential line elements in material and spatial coordinate systems are calculated by vector products of the two associated vectors as stated in these equations respectively. The area element defined in spatial coordinate system can be developed to ring the area dA, the small capital dA, with the large capital dA. And okay, this is straightforward. Here we think that there is an identity matrix between M, this symbol, permutation symbol, and the unit vector between two tensors. In this case, the permutation symbol is considered as one of spatial tensors. So between two tensors, we think there is an identity matrix. So that is denoted by these two terms. So using this formula, so we can derive the relation between the dA, the small capital dA, and large capital dA, as can be seen in this equation. And also from this relationship, we can describe the large dA in terms of small dA by this equation. In this page, we are going to link two balloons defined by three differential line segments in material and spatial coordinate systems. The balloon elements in material and spatial coordinate system are calculated by this and this formula respectively. Applying some initial notation related arithmetic formula, including this formula, so we can develop directly the balloon in spatial coordinate system to get some expression in terms of balloon in a material coordinate system. So we can obtain this final equation, which is very important for advanced mechanics. For small deformation, we can define the volumetric strain using differential tensor and displacement. And of course, strain tensor quantities should obey the transformation rule for the second order of tensor. The transformation rule for Eulerian and Lagrangian strain tensors can be stated like these equations. The element of transformation matrix Ti prime j is defined by cosine value of the angle between two axes, xi prime and xj, as can be seen in these figures. Of course, applying a simple arithmetic rule, including chain rule for partial differentiation, so we can verify this transformation law. In fact, we call this quantity tensors of order 2 because they satisfy the transformation law for the tensor order 2. Now let's study principal strain, strain invariance, and cubical dilatation. A strain vector in the direction of the unit vector n is defined by this equation. This is a inner product of the linear Lagrangian strain tensor and the directional unit vector m. If the direction of the strain vector coincident with the direction of unit vector, the direction becomes the principal direction of the tensor, and its corresponding strain component in the same direction is defined principal strain. So the principal values and directions are calculated from this eigenvalue problem. Because the eigenvalue problem is a typical homogeneous equation, the characteristic equation should be satisfied, which can be formulated as this cubic nonlinear equation. Of course, there exist 3 real number solutions, even though it is not easy to calculate them by hand calculation. There are 3 coefficients which are called Lagrangian strain invariants. Therefore, that is because the coefficient invariance, the 3 invariants play very important role because they are cognitive independent. Of course, you know, the transformation rule itself is one of the typical similarity transformation. So in similar transformation, there is no change in the eigenvalues, that is the principal values. So the equation should be the same because the equation, nonlinear equation, should give us the same solution regardless of the coordinate systems. Cubic dilatations are defined by these equations. And now let us define a diametric or a spherical linear strain tensors and discuss something for the new tensors. This term means average value of tensor quantity. That is mean value of its normal components. When we subtract this mean value from a strain tensor, we can obtain a new tensor called diametric strain tensor. Because diametric strain tensor also belongs to second order tensor, this transformation rule should be satisfied, and we can define the eigenvalue with its associated invariants in the same way with the original strain tensors. There is a special case of deformation called plane strain. In plane strain case, the strain tensor is stated like this. In this case, all strain components related with x3 axis are all 0. To meet this requirement, the displacement should be a function of only x1 and x2, and the displacement component U3 should be constant. So it is a very strict case. So it is not easy to find some application examples which meet this requirement. Then strip loading can be considered as the plane strain cases. However, theoretically it is important because we develop some theory and some equation under the assumption of a plane strain case. We have 6 independent differential equations relating displacement to strain. Let's consider the case that we try to find displacement functions from 6 given strain functions, which were independently determined. Then it may violate the one-to-one correspondence. You cannot find the solution. A kind of over-constraint problem occurs in this case. We can formulate the requirements on one-to-one correspondence as these differentiations, which are called compatibility equation. When the strain components meet these geometric compatibility equations, then we can obtain the displacement fields which meet all requirements. We can find that there are only 6 independent differential equations in these compatibility equations involving this equation. Of course, this differential equations are so complicated, but we don't have to consider this compatibility equation when we use the continuous function for displacement field in final element method. Now we are going to study logarithmic through a natural strain tensor. First, we have to define log matrix A. Log matrix A is defined by a matrix of which eigenvector should be the same with that of the matrix A, and eigenvalues should be the same with the logarithmic values of the eigenvalues of the matrix A. The logarithmic strain tensor in Lagrangian description is formulated like this. And the eigenvalues of the Green's definite tensor is the scale of the eigenvalues for the line stress tensor. So we can express the logarithmic true strain using the stress tensor. Now, let's study on stresses related with deformation gradient tensor. In spatial coordinate system, a stress vector, which means force per unit area at a point, is defined by this equation. The stress vector is defined at a point, and its value is dependent on the direction specified by unit vector n. Cauchy stress is defined by this equation. That is, the jth componentable force per unit area exerting on a plane normal to a unit vector, EI or XI axis. Now, let's define the first pure Kirchhoff stress from this requirement that the resulting force exerting on an aerial element in spatial coordinate system by Cauchy stress should be the same with that in material coordinate system by the first pure Kirchhoff stress tensor. Applying this equation, we can derive the relationship between Cauchy-Stress tensor and the first pure Kirchhoff stress tensor. Unfortunately, the first pure Kirchhoff stress is unsymmetric. By pre-multiplying the first pure Kirchhoff stress by the inverse of matrix F, that is deformation gradient tensor, so we define the second pure Kirchhoff stress like this, which became of course symmetric. From these relationships, we can express the Cauchy stress in terms of the first pure Kirchhoff stress or the second pure Kirchhoff stress. These are the summary of continuum mechanics necessary for this slide for further development of the theory. Substituting all relationships into the equation of motion in special Coulomb system, so we can get the equation of motion for the first and the second pure Kirchhoff stresses like this. Okay, assuming acceleration 0, we can get equation of equilibrium from the equation of motion for solid mechanics. Now we are going to define rate of deformation and natural strain increments. The velocity gradient tensor is defined by the partial differentiation of velocity component Bi with respect to the coordinate xj. The velocity gradient tensor can be decomposed into two parts, that is symmetric parts and skew-symmetric parts. The symmetric part is defined as rate of deformation tensor, and the skew-symmetric part as vorticity or spin tensor. Of course, we can define rate of deformation tensor by directly differentiating strain with respect to time parameter. However, we can calculate the strain component from direct integration of the rate of deformation tensor, because principal direction of the strain or deformation tensor may change from time to time. So natural strain increments, which are formulated as total differential of strain, are very useful, especially for plasticity, to calculate a small strain increment at a time instant.